Hello, this is an extra video. That means extra information that we're not going to be covering on the normal videos, but it can be useful for you to have some more flexibility when looking at power series. So this is a video that gives you an introduction to power series and some basics for the methods that we have been looking at when using power series in the ODE setting. So we're going to be looking at something that is called a power series. This is an infinite sum of powers of x times a coefficient. The coefficient is fixed, and n is just a natural number, integer. So if you write it down, that is a0 plus a1x plus a2x squared and so forth. Before looking at power series, we first look at series, so no power of x is involved, and sequences. We look at sequences are just series of numbers in which we usually know some information on how the thing is working. In this case, we will look a lot at sequences that are partial sums of the series. So we are summing cn's, but we are stopping at some point. So b0 is equal to c0, b1 is equal to c0 plus c1, b2 is equal to c0 plus c1 plus c2, and so forth. The reason why we're looking at it is that we say that a sequence is convergent if the limit of the sequence itself, so if you go at infinity through the sequence, is a finite number. Otherwise, it's called divergent. The otherwise means that either the limit does not exist or the limit is infinity. In both cases, it's called divergent. Then a series is convergent if its partial sum sequence is its convergence itself. In the case in which that is true, then we write that the series is equal to the limit of the partial sum sequence connected to it. Let's look at sequences. A very key information about a sequence, if it is the Cauchy sequence. I'm going to give you a mathematical interpretation of the Cauchy sequence and later on a graph visualization of it. So a sequence is called Cauchy is for any positive real number epsilon, there exists an integer that might depend on epsilon, such that for all integers bigger than the capital N depending on epsilon, the absolute value between the difference of Bn and Bm is smaller than the positive real number we started with. How can we look at it? Let's start by looking at the natural numbers on the x-axis and the value of the sequence on the y-axis. So at the beginning it might swing a lot, but if we have chosen an epsilon, then there exists an n epsilon such that everything after is bounded by something that is at most epsilon width. That means that any two elements you choose after n epsilon are closer than epsilon between the two of them. Visually, that means that indeed your swings are decreasing, and you can imagine that that means that the sequence is convergent. Also, the fact that you can choose any epsilon means that for any value you can just shift a bit further on in the sequence, and this width in which all elements are will just get smaller and smaller. So there is a theorem that when you're looking at a sequence in the real numbers, the sequence converges if and only if it is Cauchy. Corollary, a series converges if and only if its partial sum sequence is Cauchy itself. We have seen that they're connected. A necessary condition, but is not sufficient, is that for every epsilon bigger than 0, there exists a value such that after that value, all values of your coefficients that are added in your series are smaller than epsilon itself. It is not sufficient because you might have the situation in which you're still adding something that is getting smaller and smaller, but always in the same direction and still not converging. When we're looking looking at power series, well, we have an extra layer of flexibility because this x that is at power can make the full term being bigger or smaller depending how big x is. We say that I is an interval of convergence if for all x being in I, the power series calculated at that x is smaller than 0. It's smaller than infinity. It converges to a given value. That value obviously depends on x itself. Furthermore, if there is an interval of convergence, then the function defined by the power series on that interval is continuous. You have to set yourself in the interval because outside of the interval, that function might not exist. So let's look at a couple of properties of the interval of convergence. First of all, well, 0 belongs to the interval. It's trivial because if x is equal to 0, the only term in your series is actually a0. Then we can compute how big the interval of convergence is by finding the radius of convergence. So the interval of convergence goes from minus radius to plus radius. It might incorporate the bounds or not. That is a topic that we're not going to be seeing in this video. But whatever happens at the bound, within minus r to r, your sequence is convergent if r is defined by one of these two fractions. If the limit at the bottom of the fraction tends to infinity, we say that the radius of convergence tends to 0 and the interval of convergence is only 0. Let's look at some examples. So the power series in which for n going from 0 to infinity of n factorial x to the power n, then the coefficient of our x to the power n is n factorial, we could use one of the definitions for the radius of convergence that we had before, and we notice that, well, the limit for n going to infinity of n plus 1 factorial divided by n factorial, we can simplify it as the limit for n tending to infinity of n. 1 over that is 0. So this power series does not have an interval of convergence outside of 0 itself. It converges at 0, but as soon as you get out of it, you diverge. Let's look at another power series. This is a bit more complicated. Sum from n going from 0 to infinity of minus 1 at the power n, x plus 5 divided by 2, all of it at power n. So this one has a different format than what we have seen until now. But what we can do is introduce another variable, y, and define it as x plus 5 divided by 2. Then we can simplify the power series to be a power series of minus 1 at the power n times yn for sum over all n's. So we can find the radius of convergence for this new power series. We can see how things simplify, so the radius of convergence is 1. So the interval of convergence goes from minus 1 to plus 1 when we're looking at the series defined in y. And then we translate that interval through the transformation for x, giving us an interval that goes from 2 to 3 for I. We don't really know what happens at the boundary of this interval, but we're not going to look into that. We can look at power series as a sort of infinite polynomial, but we can look at it in that sense only on the convergence interval, because outside of the convergence interval, the power series has no sense. So everything we can do on a power series, handling it as if it was a polynomial, remembering ourselves that it's true only on the interval of convergence. So for example, we can take derivatives. So a derivative of a power series is the sum of the derivatives. We can shift the indices in such a way that the sum still goes from 0 to infinity, but this is valid only in the interval of convergence. We can do the same for integrals on the interval of convergence. So the integral has to be taken within the interval of convergence. we can sum power series. And the sum of two power series is the power series of the sum of the coefficients, only on the intersection between the two interval of convergence for the two power series. The product of two power series is again a power series. Again, only when the two power series are convergent. Let's look a little bit at what is the coefficient of the coefficients of the power series that is a product of two power series. We say that it is the discrete convolution of the sequences of the previous two power series. And this discrete convolution is defined as Cn being equal to the sum from I going from 0 to n of ai times bn minus I. That means it is a0 bn plus a1 bn minus 1 plus a2 bn minus 2 plus many terms until you get to an minus 1 b1 plus an b0. You can see how this works out on the smaller elements, because for example, when you're looking at the power of x, the zeroth powers of x, then the coefficient on the right hand side for the zeroth power of x is just a product of the two coefficients for the two zeros, the zeroth powers of x. So c0 is equal to a0 times b0. You can look at it, convince yourself if you work on the first and second coefficients again. There is an important theorem in here that two power series are the same, are equal, if and only if each of their coefficient is the same. The idea of the proof is that xn is different than xm, x to the power n is different than x to the power m if n is different than m. And you cannot adjust a coefficient in front of one of the two to make them the same. That means that x0, x1, and x2, and so forth are linearly independent. And that brings you to say that the power series are equal only if each coefficient is equal.